ಕಾಣಿಸ್ತಿಲ್ವಲ್ವಾ? ಎಸ್ ಅನುಭವ್, ಒನ್ ಝೀರೋ ಝೀರೋ ದೆನ್ ಏನಾಯ್ತು? ಗೀತಾ ಯದೆ ಶ್ರೇಯಸ್ ಅಭಿಜಿತ್
Yes, ma'am.
ಹೇಳಿ ಲೋವರ್ ಟ್ರಯಾಂಗಲ್ ಮ್ಯಾಟ್ರಿಕ್ಸ್, ಡಯಾಗ್ನಲ್ ಮ್ಯಾಟ್ರಿಕ್ಸ್ ಮತ್ತೆ ಅಪ್ಪರ್ ಟ್ರಯಾಂಗುಲರ್ ಮ್ಯಾಟ್ರಿಕ್ಸ್ ಏನೇನ್ ಬಂತು ಅಂತ.
Lower triangular matrix, ma'am, 1 0 0, 2 1 0, -1 -1 1.
ಡಯಾಗ್ನಲ್ ಮ್ಯಾಟ್ರಿಕ್ಸ್ 1 ಕಾಣಿಸ್ತಿದಲ್ವಾ? ನಾನು ಕರೆಕ್ಟ್ ಆಗಿ ಬರ್ದಿದ್ದೀನಲ್ವಾ? ಬೋರ್ಡ್ ಕ್ಲಿಯರ್ ಇದೆಯಾ? What happened? Anusha, can you tell me?
A diagonal matrix is, ma'am, 1 0 0, 0 -2 0, 0 0 -2,
0 0 -2.
-2.
Upper triangular matrix again, your diagonal elements are 1 1 1 and these are 0. Tell me the other 3 elements.
0 -1, next row 0.
Here, right?
Yes, ma'am.
Correct, Geeta?
Yes, ma'am.
So now when they ask you to do the LU factorization or the LDU factorization, this is how you have to end up your problem after obtaining all the solution to the matrix. You also need to mention A is equal to LDU form, where you have to mention the lower triangular matrix, diagonal matrix, and the upper triangular matrix. So I assume now all of you are clear with obtaining a solution to the given system of equations using LU factorization, LDU factorization, obtaining the inverse of a matrix A, identifying whether your system is consistent or not, using row reduction algorithm to find out, and also to find out the solution to the system using Gauss elimination method. Okay? Is that clear? Now, with this, let us understand one more important thing. So clear with this LDU factorization? Any doubts? All of you have done it? So I hope you all have studied what are groups in a set. Yes or no? What is a set? A set is a collection of similar data types. So I can say a set of real numbers, a set of complex numbers, or a set of natural numbers. When do I call this set as a group? You all have studied it in your other classes. So what is a group? Because ನೀವೆಲ್ಲ ಓದಿದ್ದೀರಾ ಗ್ರೂಪ್ಸ್ ಅಂದ್ರೆ ಏನು ಅಂತ. ನಿಮ್ಮ ಆಲ್ಜಿಬ್ರಾದಲ್ಲಿ ನಿಮ್ಮ ಸ್ಕೂಲಿಂಗ್ ಅಲ್ಲೇ ಕಲ್ತಿರ್ತೀರಾ ಗ್ರೂಪ್ ಅಂದ್ರೆ ಏನು ಅಂತ. ಏನು ಗ್ರೂಪ್ ಅಂದ್ರೆ? ಭೂಮಿಕಾ, ಭೂಮಿಕಾ ರಾಣಿ, ಭೂಮಿಕಾ.
Yes, ma'am. Yes, ma'am.
ಗ್ರೂಪ್ ಅಂದ್ರೆ ಏನು ಭೂಮಿಕಾ? ಓದಿದ್ದೀರಾ ಅಲ್ವಾ ಎಲ್ರೂನು? Yes, Arjun. So if you don't respond, that tells me that you are not present in the class. That's it.
Yes, ma'am.
Okay.
Hello.
Yes.
Hello.
Yes, Arjun, tell me.
ಅದೇ ಮ್ಯಾಮ್ ಇದು ಇಂಟರ್ನೆಟ್ ಕಟ್ ಆಗೋಗಿತ್ತು ಅದಕ್ಕೆ ಲೀವ್ ಆಗುತ್ತೆ.
Okay. So group ಅಂದ್ರೆ ಏನಪ್ಪ? So ನೀವೆಲ್ಲ ಓದಿದ್ದೀರಾ ಇದನ್ನ, I'm not asking something new. When do I say a set forms a group? So you remember, you can say set forms a group under addition, or a set S forms a group under multiplication. ಬರ್ದಿರೋದು ನೆನಪಿಲ್ವಾ? When do I say this form a group under addition or multiplication? You all have understood you all know what is a group or not? ಗೊತ್ತಿಲ್ವಾ? ಅಡಿಷನ್ ಬರ್ತಿರೋದು ನೀಟಾಗಿ ಕಾಣ್ತಿದ್ಯಾ? Yes. ಅರ್ಜುನ್ ಕಾಣಿಸ್ತಿದ್ಯಾ? ಅರ್ಜುನ್ ನೀಟಾಗಿ?
ಎಸ್ ಮ್ಯಾಮ್.
ಗ್ರೂಪ್ ಅಂದ್ರೆ ಏನು? ಎಲ್ಲರೂ ಓದಿದ್ದೀರಲ್ವಾ? ಯಾಕೆ ಎಲ್ಲರಿಗೂ ಮರ್ತೋಯ್ತಾ? When I say it is a group under addition, I'm just telling the conditions for it for some set yes, because I need not discuss about what is a group and other things now. Just for your understanding, when I say the set S forms a group, say if I assume the set S to be some numbers, or I'll make it generic, set S is a set of real numbers. Okay? If I have to say that this set S forms a group under addition, I need to check with certain properties. What is the first property here? I need to check whether the sum of two elements in this set S belongs to that. Say for example, for all A plus B belongs to S. So when you add any two real numbers, will you get back the real numbers? Yes or no? So I can say that this is satisfied. When I add two real numbers, I'll get back a real number. So again, it is present in the given set, yes. And then I also check whether it is commutative. So you all know addition of two scalars is always commutative. Right? Addition of two scalars is commutative, and even this is satisfied. And also, first thing is the sum has to be present in the given value, and then I need to check the commutative property. So yes, it is commutative. Either way, I add the two real numbers, the result is same. And then I also need to check whether it is associative. How do I check the associativity property? A plus B plus C is equal to A plus of B plus C. So we all know that either way I add it, I get back the same result. So which is my additive identity. So I need to check whether there is an additive identity in the group. Which is your additive identity? Which is the additive identity? ಏನೆಲ್ಲ ನಿದ್ದೆ ಮಾಡ್ತಿದ್ದೇನಪ್ಪ ಲಾಸ್ಟ್ ಕ್ಲಾಸ್ ಅಂತ. Additive identity is 0. So 0 is present in the set of real numbers. Is 0 present in the set of real numbers? Yes. And then, do I have additive inverse? What I mean by additive inverse, say for all A, all A belonging to yes, there is another where other value B belonging to yes, such that A plus B is equal to 0. This indicates that B is equal to minus A. Since we all know that the real numbers are both positive and negative numbers, so this is also possible. So when all these conditions are satisfied, then I say that this set of real numbers, the set of real numbers forms a group under addition. So this set of real numbers forms a group under addition. Is it clear? Any doubts? Similarly, if I say it forms a group under multiplication, what all I need to check? Whether the product of two elements exists? Yes. A scalar multiplication is associative? Yes or no? I want you guys to respond. ಅಥವಾ ನಿದ್ದೆ ಮಾಡ್ತಿದ್ದೀರಾ ಮೂರುವರೆ ಕ್ಲಾಸ್ ಅಂತ. So multiplication is associative, multiplication is commutative. Your multiplicative identity is 1. And then once I get my multiplicative identity as 1, what is the next value? I need to check for the inverse. Your real numbers can also be fractions. So the inverse of a matrix also exists. So I can say the set S also form a group under multiplication. Is it clear what are groups? Any doubts? Having understood what are groups, then we will get into what are fields. Artha aita groups andre enanta? Akhilesh? Amrita?
Yes, ma'am.
So shall I clear this and we'll start with the fields? It is just a recap of which you had already studied in your schooling only. Okay? So board is also visible clearly, right? I hope there is no issue for viewing the board. Now, let us understand what are fields. When I say it's a field that is similar to a group, so first let us understand what are fields. Okay? So when I say what are fields, I just denote any field with a character F. Now, to say my F forms a field, I need to check with certain properties. So what are those properties? So let us consider this F to be a set of real numbers or the set of complex numbers. Is it clear? So let F denotes a set of, instead of taking it as B, just take let F denotes a set of real numbers or the set of complex numbers. So when I have to say that the given set of numbers or given set is a field, it should also satisfy certain conditions, as I said, for a group. What is the first condition over here is addition is commutative. Is it clear? The very first condition is the addition is commutative. And that when I say the addition is commutative, it is same as x plus y is equal to y plus x for all x comma y belonging to the set F. Currently, I'm not calling it as field because I'm not still checked for all the properties of my field. What is the next thing? Next property is I should also check whether addition is associative. Is my addition associative with real numbers and complex numbers? Yes, so I can say x plus y plus z is equal to x plus of y plus z for all x comma y comma z belonging to F. Is that clear? So now I check for addition is commutative and associative. Now I check whether there is an additive identity in the set F. Okay. So there is, do you have a unique additive identity over here? Yes, my additive identity exists. There is a unique element 0 in the set of F, where when I add it with that element, I get 0. There is always a unique element 0 in F such that x plus 0 is equal to 0 plus x, which is equal to x belonging to F. That is, or I can say to be more specific, instead of telling it belongs to F, for every value of x. Okay? So for every value of x, there exists an additive identity. But that doesn't satisfy again. I also need to check for additive inverse. So for all value of x, it has a unique element. I'm not writing everything on the board. For each value of x, there exists a unique element minus x such that when I add x with minus x, I get the 0 vector. Sorry, 0 element. Here I'm dealing with scalars. I'm sorry for that. So for each vector in x, there exists a unique vector minus x. When I add these two vectors, I get the 0 vector. Is that clear? And next, the fifth property is I check whether multiplication is commutative. Kindly take down all this because you will need to multiplication is commutative. When I say multiplication is commutative, x into y is equal to y into x for all x comma y belonging to set F. Similarly, after telling multiplication is commutative, which is a property I need to check again. Multiplication is associative. That is, I have xy of z is equal to x into yz for all x comma y comma z belonging to F. Okay. Similar to this, what is the next thing I need to observe now? What is the next thing? I need to check whether the multiplicative identity exists. Which is the multiplicative identity? 1. So I need to check whether there is a unique element 1 which exists in the given set such that x into 1 is equal to x. For all values of x is equal to 1. Is that clear? And next, I also need to check whether the inverse of multiplicative inverse exists. That is, for every x in f, there exists 1 over x in f such that x into 1 over x would give me 1. That is nothing but x into x inverse is equal to 1. Okay? And then with all these 8 properties, with these, can I say that it's a group under addition with the properties 1 to 4? Similarly, with the properties 5 to 8, I can say that it also forms a group under multiplication. Now let us consider the 9th property, which I say we check for whether the multiplication distributes over addition. So the 9th property is multiplication distributes over addition. Is that clear? So that means x into y plus z is equal to xy plus xz for all x comma y comma z belonging to set F. Yes. After satisfying all these 9 properties, it also need to check, okay, the set F of objects x, y, and z. It should also have 2 operations, that is your addition and multiplications. As I said already, for all values of x comma y, x plus y has to belong to the set F. So that is addition operation need to be satisfied. So when the addition operation is satisfied, for all x comma y, x plus y belongs to F. Similarly, for all x comma y in multiplication, xy belongs to F. So this forms a group under both addition as well as it forms a group under multiplication. So if the F together forms which can form all these properties, that means I can say if set F forms a group under addition as well as a group under multiplication, then I call such as a field. That is the set F together with the addition and the multiplication operation is called as a field, where I represent the field as F with plus and, where I represent the field with F, which is closed under addition as well as multiplication. Is that clear? That is how I represent my field. Any doubts with this? What is a field and how do you represent a field? Yes? Any doubts, guys? Shall I proceed further? Okay. So now with this, can you now tell me whether the set of complex number forms a field or not? Yes. With this, can you just tell me set of complex number forms a field or not? So is your addition commutative? In the complex numbers, when you add two complex numbers, you again get a complex number which is present in the field. Is it not? And then again, what is the next property? When I add three complex numbers the either way, I get a complex number again. Right? And then what is the other one? Yes, please. Do you have a zero element in the complex number? Yes. Do you have a negative element in the complex number? Say for example, I have 2 plus 3i is my complex number. Minus 2 minus 3i is also my complex number. So when I add these two, I get 0. Is it not? So the complex number also exists. The inverse exists. When you multiply two complex number, you get a complex number again. That is also there. And then your multiplication is commutative. Either way I multiply my complex number, the answer remains the same. Similarly, whether your multiplication is associative, yes. Yes, the either way I multiply the two complex numbers or three complex numbers, the result is same because it's not a vector. These are all scalars. Either it's a real number or a complex number, all these are scalars. Okay? And then I have one element where if I say my complex number is in the form of a plus ib, where b goes to 0 and a is 1. So I have the additive identity, I have the inverse, and when I multiply it, multiplication distributes over addition. And when I add two complex numbers, I get a complex number. And when I multiply two complex number, I get a complex number. So can I say now the complex number is a field under addition and multiplication? Yes? Can I say that? Yes, any doubts still here? No? So shall I clear this? So have you all understood what is a field? Now tell me, is the set of natural numbers a field? Tell me whether the set of natural numbers is a field or not. Yes? What does your natural numbers contain? What does your natural numbers contain? Basic numbers are markalta. Huh? Yes, Sinchana. Visual. Chetana. Natural numbers ಅಂದ್ರೆ ಯಾರಿಗೂ ಗೊತ್ತಿಲ್ವಾ 60 ಜನದಲ್ಲಿ ಏನ್ ನ್ಯಾಚುರಲ್ ನಂಬರ್ಸ್ ಅಂದ್ರೆ ಓಕೆ ಇನ್ ನ್ಯಾಚುರಲ್ ನಂಬರ್ಸ್ ಅಂದ್ರೇನು all positive integers, yes. So now the answers are coming. I think You guys are sleeping? Are you all awake? Numbers starting from 1 to infinity. So all positive integers. So definitely this cannot form a field because there is no minus x. Alright? And also there is no 0 is neither a natural number. Right? Now you all have understood what is a field. Now let us see what do you mean by a subfield? ಕಾಣಿಸ್ತಾ ಇದೆಯಾ ಬೋರ್ಡ್? You all understood what is a field. Now let us understand what is a subfield. What is a subfield is nothing but a subset of field F. Say for example, I took a complex number and we all saw that the complex numbers forms a field. Is it not? We took the set of complex numbers and we all observed that the set of complex numbers forms a field. So in that, I take a subset. So can I say real number is a subset of complex number? Yes or no? Yes, can I make that statement where I say the real number is a subset of complex number? Now, if this is my field and in that I take a subfield of real numbers and in this subfield I check whether only real numbers will form a field or not. Only real numbers forms a field or not. Can you tell me only the real numbers will form a field or not? Hello? Yes, can anyone tell me? Check for all the properties of a field and tell me whether the real numbers is a field or not. Quick. I'll give you 2 minutes time. Set of real numbers field down. Yes. A set of real numbers forms a field. And this set of real numbers is a subset of complex numbers. Are you getting it? The set of your negative numbers are also zeros are that. Your real numbers is a subset of complex numbers and this itself is a field. Then I can say real numbers is a subfield of complex numbers. That is, I take a subset from the field and check whether that subset itself will form a field. If the subset itself will form a field, then I can say the subset is a subfield under the set of complex numbers. Is that clear? You can take down the definition of a subfield. I take it with respect to the same example of complex numbers. The subfield of the field C, a subfield of the field C, I was taking it down. A subfield of the field C is a set F of complex numbers, which is itself a field which is itself a field under the usual operations of addition and under the operations and usual operations of addition and multiplication of complex numbers. Is that clear? Any doubts? So a subfield of the field C is a set of F of complex numbers, which is itself a field under the usual operation of addition and multiplication. So how do I say that R is a subset? So if I represent my complex number in the form of A plus IB, if my B value goes to 0, the B value is equal to 0, so then I get all the complex numbers of the form A plus I0, that is nothing but A. So all these are my real numbers. Is that clear? Now I'll give you a task, okay, to check whether the positive integers form a field. Does the positive integers form a field? Or at least can you tell me a set of integers will form a field or not? Quick, let me see who will answer first. Everything will be recorded here. Is your positive integers a field? No. Why? Why is it not a field? Yes, you all said it's not a field, right? So you have to justify why it is not a field. The inverse like natural numbers, okay. What about integers? Do they form a field? Okay, you all said me that the set of positive integers will not form a field. What about integers? Will they form a field? So whatever I'm writing in the blue marker, is it visible clearly? Syed. Syed Naman. Shruti. Set of integers field agata. No. Yes, correct, Bijwal. Because you don't have the multiplicative inverse in the set of integers. So with this, I assume you all have understood what are fields. Yes. And now, with this, we'll begin the next chapter, which is your vector spaces. So this completes your first unit. Any doubts in the first unit? So whatever the problems I gave you in the last class also, right, on LU factorization and LDU factorization? Yes or no? Kotna illappa? Okay, take down the problem. So how many problems you have for this week to solve? Yes, Shreyash? Visual? You guys are there or not? So I gave some problems based on obtaining the solution by using inverse of a matrix, right? I gave 3 problems in the last class, where that's also available in your textbook, sorry, in your notes, which is uploaded in the classroom. ಎಲ್ರಿಗೂ notes ಸಿಕ್ಕಿರ್ಬೇಕಲ್ವಾ? And one more problem, the second problem, to find out the solution to the system of equations given the matrix A and matrix B. And the other one is your LU factorization, sorry, LDU factorization. Take down the matrix, which is 2, 4, -6, -2, -8, and -10, -6, -32, and -66. So obtain the LDU factorization. So there are 5 problems which you have to solve it and upload it in the tutorials in the classroom. I'll be posting a new assignment. Okay. So in that you guys need to post your answers by solving the problem for LDU factorization and inverse of a matrix along with LU factorization. Okay, Martinan. So let's begin the next module, which is your vector spaces. I'm telling you in the beginning itself, this unit is not so easy. Better you don't miss any classes. Okay? So let us see what are vector spaces. Any doubts till here? You have it till here for your internals. Internals next week alva. Timetable bantu ankoತೀನಿ already. ಬಂದಿಲ್ವಾ? ಅನುಭವ್?
Yes, ma'am.
Timetable ಬಂದಿಲ್ಲ ನನ್ನ ಎಕ್ಸಾಮ್ದು?
ಮ್ಯಾಮ್ ಡೇಟ್ ಗೊತ್ತಾಗಿದೆ, ಇದೆ ಅಂತ ಗೊತ್ತಾಗಿದೆ, ಸಬ್ಜೆಕ್ಟ್ ಯಾವತ್ತಿದೆ ಅಂತ.
ಓಕೆ. ಕಾಲೇಜಿಂದನೇ ಹಾಕಿಲ್ವಾ? ಏನ್ ನಿದ್ದೆ ಮಾಡ್ತಿದ್ದೀರನ್ರಿ ಅನುಭವ್?
ನೋ ಮ್ಯಾಮ್.
ಮತ್ತೆ ಕಾಲೇಜಿಂದನೂ ಬಂದಿಲ್ವಾ ಅಂದೆ?
ಇಲ್ಲ ಮ್ಯಾಮ್.
Sorry, anyway, my subject will be the first one. Okay, so now let's start with the second unit, which is known as your vector spaces. For this, I'll be referring two books. One is your David C. Lay and Hoffman and Kunz. Kenneth Hoffman and These are the two books we will be referring it for what is known as a vector spaces. So meanwhile, I want you guys to see a video on vector spaces. Okay? Just a moment. So to understand what is a vector space,
of something deeper. On the one hand, defining vectors is primarily the transformed versions of the basis vectors in that same. The only term that can Okay, in this video, I want to start talking about vectors. We'll decide instead on which two operations. So multiplication with a circle. In some other videos, we'll go. Just know that letter. You probably first encountered vectors in physics, where they are commonly used to describe forces. In science, a vector is an arrow with a length and a direction. You can have two-dimensional vectors which live in the plane, or three-dimensional vectors which are more appropriate scale a vector. You probably first encountered vectors in physics. You probably first encountered.
Encountered vectors in physics, where they are commonly used to describe forces. In science, a vector is an arrow with a length and a direction. You can have two-dimensional vectors.
is it audible, guys? Yes? ನಿತೀಶ್ ಕೇಳಿಸ್ತಿದ್ಯಾ ದ ವಿಡಿಯೋ ಪ್ಲೇ ಮಾಡ್ತಿರೋದು
which live in the plane, or three-dimensional vectors which are more appropriate for the three-dimensional space that surrounds us. Taken together, we call the collection of vectors a vector space, but you can generalize this idea and find countless other uses for vector spaces. In the plane, a vector is described by a pair of numbers, the x-coordinate and y-coordinate. It's assumed that the tail of the vector is at the origin, while the head of the vector is at the given coordinates. We call all the vectors in a plane a two-dimensional vector space, because it takes two numbers to describe each vector. You can add any two vectors to get a third vector, and if you multiply the coordinates by a number, you can scale a vector. Similarly, you can have vectors with three coordinates, an x, y, and z coordinate. Once again, the tail of the vector is at the origin, and the head is at the point given by the three coordinates. Like before, if you add two vectors in three-dimensional space, you'll get a third vector, And again, you can scale vectors by multiplying the coordinates by any real number. All of these vectors form a three-dimensional vector space because it takes three numbers to describe each vector. It's tempting to think that two- and three-dimensional vector spaces are all that we really need. Perhaps a fourth dimension if you work in space-time. But this is abstract algebra, and our goal is to generalize things as much as possible without sacrificing usefulness. For example, imagine an alternate universe with 10 dimensions. Taking inspiration from two- and three-dimensional vector spaces, we could suggest that in this universe, forces could be described by a list of 10 numbers. And like before, you can add and scale vectors. We would call this 10-dimensional space. If you were to generalize this further, you could say n-dimensional space is a place where forces are described by vectors with n coordinates. We call this n-space. Let's stop for a moment and look at what properties all of these vector spaces have in common. For starters, you can add any two vectors, so there's an operation, addition. Better still, the order in which you add vectors does not matter.
Vector addition is commutative. There is a zero vector, which doesn't point in any direction. Adding zero.
Yes, did you all guys understand what is a vector space to some extent at least? Echoing. Oh, Spandana, I think I should have muted the audio over here. Okay, I'll just rectify it again.
Welcome back to linear algebra. Today we're going to introduce the first bit of our more abstract hierarchies. So here are vector spaces. So working with specific vector space.
Ma'am, video is not visible.
Yeah, I've not shared the video. Only the audio is coming, I guess, right?
Yeah, yes, ma'am.
So now I've muted my audio so that there won't be any echo, and I'll be presenting with this video.
I'd like to revisit a deceptively simple question that I asked in the very first video of this series. What are vectors? Is a two-dimensional vector, for example, fundamentally an arrow on a flat plane that we can describe with coordinates for convenience? Or is it fundamentally that pair of real numbers, which is just nicely visualized as an arrow on a flat plane? Or are both of these just manifestations of something deeper? On the one hand, defining vectors as primarily being a list of numbers feels clear-cut and unambiguous. It makes things like 4-dimensional vectors or 100-dimensional vectors sound like real, concrete ideas that you can actually work with, when otherwise an idea like 4 dimensions is just a vague geometric notion that's difficult to describe without waving your hands a bit. But on the other hand, a common sensation for those who actually work with linear algebra, especially as you get more fluent with changing your basis, is that you're dealing with a space that exists independently from the coordinates that you give it, and that coordinates are actually somewhat arbitrary, depending on what you happen to choose as your basis vectors. Core topics in linear algebra, like determinants and eigenvectors, seem indifferent to your choice of coordinate systems. The determinant tells you how much a transformation scales areas, and eigenvectors are the ones that stay on their own span during a transformation. But both of these properties are inherently spatial, and you can freely change your coordinate system without changing the underlying values of either one. But if vectors are not fundamentally lists of real numbers, and if their underlying essence is something more spatial, that just begs the question of what mathematicians mean when they use a word like space or spatial. To build up to where this is going, I'd actually like to spend the bulk of this video talking about something which is neither an arrow nor a list of numbers, but also has vector-ish qualities: functions. You see, there's a sense in which functions are actually just another type of vector. In the same way that you can add two vectors together, there's also a sensible notion for adding two functions, f and g, to get a new function, f plus g. It's one of those things where you kind of already know what it's going to be, but actually phrasing it is a mouthful. The output of this new function at any given input, like -4, is the sum of the outputs of f and g when you evaluate them each at that same input, -4. Or more generally, the value of the sum function at any given input x is the sum of the values f of x plus g of x. This is pretty similar to adding vectors coordinate by coordinate. It's just that there are, in a sense, infinitely many coordinates to deal with. Similarly, there's a sensible notion for scaling a function by a real number. Just scale all of the outputs by that number. And again, this is analogous to scaling a vector coordinate by coordinate. It just feels like there's infinitely many coordinates. Now, given that the only thing vectors can really do is get added together or scaled, it feels like we should be able to take the same useful constructs and problem-solving techniques of linear algebra that were originally thought about in the context of arrows in space, and apply them to functions as well. For example, there is a perfectly reasonable notion of a linear transformation for functions, something that takes in one function and turns it into another. One familiar example comes from calculus, the derivative. It's something which transforms one function into another function. Sometimes in this context you'll hear these called operators instead of transformations, but the meaning is the same. A natural question you might want to ask is what it means for a transformation of functions to be linear. The formal definition of linearity is relatively abstract and symbolically driven compared to the way that I first talked about it in Chapter 3 of this series. But the reward of abstractness is that we'll get something general enough to apply to functions as well as arrows. A transformation is linear if it satisfies two properties, commonly called additivity and scaling. Additivity means that if you add two vectors, v and w, then apply a transformation to their sum, you get the same result as if you added the transformed versions of v and w. The scaling property is that when you scale a vector v by some number, then apply the transformation, you get the same ultimate vector as if you scaled the transformed version of v by that same amount. The way you'll often hear this described is that linear transformations preserve the operations of vector addition and scalar multiplication. The idea of grid lines remaining parallel and evenly spaced that I've talked about in past videos is really just an illustration of what these two properties mean in the specific case of points in 2D space. One of the most important consequences of these properties, which makes matrix vector multiplication possible, is that a linear transformation is completely described by where it takes the basis vectors. Since any vector can be expressed by scaling and adding the basis vectors in some way, finding the transformed version of a vector comes down to scaling and adding the transformed versions of the basis vectors in that same way.
Okay, fine. So ಇದರಲ್ಲಿ ಏನಾದ್ರು ನಿಮ್ಗೆ ವೆಕ್ಟರ್ ಸ್ಪೇಸಸ್ ಅಂದ್ರೆ ಏನಂತ ಅರ್ಥ ಆಯ್ತಾ? As I'm asking you guys.
In the last video, I started with this matrix right here.
Yes. So somebody said yes, Shreyas. What about others? ಏನ್ ಅರ್ಥ ಆಯ್ತು ಶ್ರೇಯಸ್ ವೆಕ್ಟರ್ ಸ್ಪೇಸ್ ಅಂದ್ರೆ? To some extent, anyway, I'll be explaining it with the definition, how I define my vector space and all. Yes. What is it you have understood? You all have understood something, right? Something or nothing? At least tell me that. Yes, Chetan, Sinchana. Pujita. But ಯಾರಿಗೂ ಅಟೆಂಡೆನ್ಸ್ ಇಲ್ಲ. ಈಗ ಯಾರ್ಯಾರು ಚಾಟ್ ಬಾಕ್ಸ್ ಅಲ್ಲಿ ರಿಪ್ಲೈ ಮಾಡಿದ್ರೆ ಅವ್ರಿಗೆ ಮಾತ್ರ. Okay. Yes, what about others? Okay, fine. If you guys don't want to respond, I'm not responsible anyway. Only visual, Shreyas, Monisha, Anusha, and Geeta are present for today's class. Thank you.